Alright, so we're going to do another example that's going to lead us into the graphs of inverse functions. So now here's the thing. We've been talking about inverse functions like everybody's got one, but here's the deal. Not all functions have inverses. Alright, not all functions have inverses. This is something that we've kind of skirted around up until now, but not all functions have inverses. For example, f of x being x squared. Does this have an inverse? Well, before you get too excited and insisting that it does, let's do some work. We're going to switch the x and y's. Alright, so we've got x equals y squared, and I want to solve for y. Square to both sides, and I add my plus or minus. Right? Now this is a problem. This plus or minus is a problem. So remember what we said about things with a plus or minus? Is this a function? Is this a function? The answer is no. Remember, we talked about if you have to graph this on your calculator, you'd need to have 2 lines on the graphing calculator in order to graph this. If you need 2 lines on your graphing calculator to solve it, it's not a function. Plus or minus. Remember, if I give you x, let me do these little tables. If I give you x is 9, then you don't know whether I want you to give me plus 3 or minus 3. So one x leads to 2 different y's. So therefore, it's not a function. It's not a function. So how do we know in advance whether or not something has an inverse? Okay. How do we know if a function has an inverse? Well, let's look at some of the stuff that we know that does. So we did know that we had f of x was 7x minus 5. We did that in a previous example, and it had an inverse, and whatever it was, it had an f inverse of x plus 5 over 7. We had x cubed plus 1, and that had an inverse of cube root of x minus 1. And we also did f of x was equal to 5 over x plus 4. And that had an inverse of something or other, 5 over x minus 4. So all those had inverses. So let's graph them and see what they had in common. So we have 7x minus 5. Oops, that's not what I meant at all. Thought I was in there. 7x minus 5. We'll graph it. Alright, so it graphs like a line, right? So I remember I figured out how to do this. I was super proud. So this is my graph of that guy. So you can sketch that in. Then I had x cubed plus 1. So let's graph that one. X cubed plus 1. And it looks like that. Alrighty. That's my x cubed minus 1. X cubed plus 1, sorry. Alright, then I had 5 over x plus 4. 5 divided by x, and that whole thing plus 4. And it looks like that. It has that, remember, it has an asymptote. Okay. So there's that. All of these had inverses, right? All of those had inverses. Now we said f of x, x squared, doesn't have an inverse. So let's see what happens when we graph that guy. Well, we should know what this looks like by now, but x squared. And it looks like that. Oops. This guy doesn't have an inverse. So what do all these that do have an inverse have in common? Can you tell by looking at them? Maybe, maybe not. So if you remember before, we talked about the vertical line test, right? Do you remember the vertical line test? The vertical line test said that it's a function if it doesn't touch any vertical line more than once, right? That was the vertical line test. Well, so all of these that we're looking at right now, these are all functions, right? They all pass the vertical line test. Vertical line, vertical line, vertical line, vertical line, vertical line. Only it touches it in one spot. Vertical line test. They all pass the vertical line test. You will be excited to know, let's scoot this over a little bit. No? Okay. You'll be excited to know that there is also something called a horizontal line test. And the idea behind a horizontal line test is that if it doesn't touch a horizontal line, any horizontal line, more than line, not time, line more than once, then it has an inverse. There's a very specific reason for this, but if it passes the vertical line test, if it doesn't touch any horizontal line more than once, then it does have an inverse. So like if you look at this one, as I run my horizontal line, it's actually more of a horizontal rectangle, but as I run the horizontal line more than once, it doesn't hit that line more than once, right? It only hits that line once. Same thing here. Even here, it's actually a perfect match, but it never hits this line more than once. Same thing here. Come here. Hey, little guy. Come here, my little horizontal line. So even here, anywhere I go, see, now it's not touching either of them. Now it's barely touching. It only touches the line in exactly one spot. As opposed to this one, where I've got bang, bang. I hit it in two spots. So if I hit a horizontal line in two spots, that means that I don't have an inverse. So you can use the vertical line test to tell if a function has an inverse. Another way of talking about whether or not a function has an inverse is we say that it's one-to-one. If a function has an inverse, it's called one-to-one. And the reason we call it one-to-one is what we really mean is 1x to 1y and 1y to 1x. So the theory is that if you give me an x, I'll give you exactly 1y. If you give me 1y, I can give you exactly 1x. The graphs, they pass the vertical line test and they pass the horizontal line test, and that's how you find functions that are inverses of each other. It's just kind of the way things work. So function is one-to-one. If I give you 1x, you can only give me 1y. If I give you 1y, you can only give me 1x back. So there's not an option. So like with x squared, if I said that x squared was 9, so if my y was 9, you wouldn't know whether or not to give me x equals 3 or x equals -3. So therefore, it's not a one-to-one function. It's not, it doesn't have an inverse. It's not one-to-one. It doesn't pass the horizontal line test. All these things mean the exact same thing. So you'll have some problems where you look at them and they'll say, okay, well, tell me if this function could have an inverse. So which of these functions has an inverse? So which ones of these functions has an inverse? So I'll give you 4 functions. I'll make it bigger. I have plenty of space. So which ones of these functions have an inverse? And if I go like that. So does that function have an inverse? Does that function have an inverse? Little thing where we go up the horizontal line, hits it only one place, hits it only one place, hits it only one place. So yes, that definitely has an inverse. What about this one? Parabola. Is that one going to have an inverse? Bring my line down. Hits, doesn't hit, doesn't hit, hits in one place, and bam. It hits in multiple places. Hits here, hits here. So, no, that one doesn't have an inverse. What about this one? Well, that's not even a function, is it? So, I think it's pretty clear right there that no, it definitely hits in more than one spot. No. Saying not even a function. That was kind of tricky. You do have some that'll look like this, though. All right? It doesn't matter if the slope changes. It doesn't matter if it flattens out in the middle. As long as I run my horizontal line, that I only hit it in exactly one spot. So this one definitely passes the vertical line test. So yes, since this one passes the vertical line test, hello, we can say that it does have an inverse. Now the last thing we want to talk about when we talk about the graphs of functions is to talk, or graph of inverses and inverse functions, is how they're related. All right. So we've been looking at, we had up here, we had these pictures of these graphs. Okay. So I'm actually going to copy these and pull them down so you can kind of take a look at them. Did I get them all? Yes. Copy. Pull them down here. I'm going to paste. Paste. Hey. There we go. All right. Just missing that little back right there. All right. So what we had here really was this one was just a graph of the blue ones, of the functions. So that's the graph of the functions, right? So those were those belong to it. Good? So now what I want to do is I'm going to graph the inverse functions and put the graphs right next to them so you can kind of see what's going on. So I'm going to graph, first of all, the inverse of this first one was x plus 5 over 7. So let me graph parentheses x plus 5 over 7. Oops, divided by 7. I'm going to graph that. Okay, so I'm going to pull this off and grab it. Right here where you can see it. Okay, now I'm going to graph the cubed root of x minus 1. And let's see, do I have a cubed root button? I do. Alright, so I'm going to go clear this out, and I'm going to go to my cube root button, which is right there, which is my cube root of x minus 1, and graph it. Okay, it looks like that. Pull this guy over. Hoping you're going to see a pattern here. So the last one is 5 over x minus 4. Where's my graph? Yeah. 5 divided by x minus 4. Graph that. And pull them off. Right. So here's what I want you to notice. You see these graphs? They look kind of similar, don't they? Do they look kind of similar to you? Maybe, maybe not. They should look kind of similar. The idea is now if I start in this bottom corner and I draw a line to this top corner, I can't do it quite perfectly because of my goofy computer. But if I draw this line here, I'll make a copy of it because I did it pretty good actually. I draw it. Oh, goodness. Right there. This is the y equals x line, right? Slope of 0, y-intercept of 0. If you look, if you're careful, you could see that this line right here, this line right here is the same thing as this line, but flipped, like that. If I took this line that I just drew here and copied it, well, no, well, I'll go ahead and do that. If I pasted it up here, where does it go through? It goes right there. You see how it's like I took this line and then I just flipped it over that line to make that one? You see where that's coming from? Let me try again. We'll do it on this next one, see if it helps it become more clear. Oops. Helps it become more clear. So this is my y equals x line. Goes right down the middle. So I have this blue line here, which is my original function. Then I have my inverse, like that. Now I'm claiming, that my inverse function looks just like my original function, except flipped over that y equals x line. So again, comparing it along this line, I'm saying if you flipped this across this line, that each one is like a mirror image. So if this was a mirror, and that's how you get that other one. Right? We'll try it one more time. In fact, I'll just grab this line right here, so we're not using it. I have this one right here, and I've got my blue line going like this, and like this. This line here is that one, but flipped. So take this, those two lines, copy, paste. Ooh, I didn't want the whole thing. I just wanted little lines. It shouldn't matter. Yeah, it's obviously going to matter, actually. Copied. And let's see, where was it? It was right there. Right there. Can you see this? If this is a mirror, how the one line and the other line, the two lines are like reflections of each other. So that's what we're kind of looking at here. Inverse functions and their inverses. Reflect across the y equals x line. Okay, they reflect across the y equals x line. They're like a mirror image across the y equals x line. So that's actually kind of cool. I like it. So part of the reason this matters is if you're doing your homework and they're asking you to choose, choose the graphs and their inverses off of looking at a graph, if one of them goes like this and the other one goes like this, then you might say, okay, those are probably inverses because they're, right here along the line. But on the other hand, if one of them goes like this and the other one goes like, you know, this, then you know that these are probably not inverses because they don't reflect across that line, you know. So the only way for this graph over here to have an inverse, let me draw a little bit better. The only way for this graph to have an inverse is if it matches a mirror reflection on the other side. If it doesn't match a mirror reflection, you know, like going like this, that's not a mirror reflection across the x-axis. It has to be a mirror reflection. So like that wouldn't work. It has to be reflected again across the mirror. So none of these options that I'm drawing in here, none of those are going to be considered inverse functions. Inverse functions have to reflect perfectly across the x equals y, the y equals x axis for this to work.